In this paper, we are trying to propose like learning scheme, basically based on the structure of the network, not like machine learning techniques. The structure of the network is a mixture of two existing schemes. The outline of my presentations: wireless sensor network and its challenges, compression, especially our concentration is on predictive coding, learning schemes in wireless sensor network. Again, it mainly concentrate on predictive coding, proposed approach, results, and conclusions. What is wireless sensor network? Wireless sensor network is composed of large number of sensor nodes which are densely deployed either inside the phenomena, that means the environment where we're trying to sense something, or very close to it. This is an sample sensor node. This is Telos B from UC Berkeley, and this is an sample wireless sensor network. These nodes have the capability to sense, compute or process, and communicate. So they have three main functions: sensing, processing, and finally communication. So these are the samples, like some snapshots of applications. They have a list of applications. I just try to manage in some figure. This is battlefield surveillance. This is environmental monitoring, especially volcano eruption monitoring. This is in intelligent transport system. This is smart factories or smart homes, and this is in our daily life. To apply this as a wireless sensor network in this huge list of applications, this network has to face a number of challenges. These challenges are like this, mainly four of them, and the first one is limited power supply or limited battery or limited energy. Second one is limited memory, and third one, processing capacity, and finally the communication bandwidth. And out of these four, power supply or energy is the main. So most of the tasks in this area, they are concentrating on how to minimize energy consumption. Similarly, we are trying to do the same here. So compression can be useful in minimizing the energy consumption, especially in communication. So energy consumption dominated by the radio communication. Like 1 bit of radio communication can be equal to like 100 to 1,000 bit of processing. So the ratio between communication and processing can be 1,000 times. So the policy here is to increase computation at the cost of minimized communication. So we need to process, like we can have some little complex algorithm so that can minimize the communication. So the policy is here: reduce communication at the cost of increased computation. So we are trying to do the same here. And communication cost is directly proportional to the number of bits we are transmitting within the network. So our plan is to reduce the number of bits to be transmitted within the network. And the compression can reduce the communication energy and hence increase the network lifetime. So if we install some network, wireless sensor network, maybe in like some battlefield, maybe in a desert, it's not possible for us to go there every day, maybe every month, to check whether the battery is okay or no. These are inaccessible areas. So we need to have some scheme that can long for like at least for our targeted days. So we need to have something that can minimize the energy consumption and give us some expected lifetime of the network so that it can match the required lifetime for the application. And one of the compression technique is predictive coding or prediction-based data gathering. So what is predictive coding? It exploits the inherent temporal correlation between consecutive readings of a sensor to predict future observation at the sink. Sink means the central node or base station, based on the statistical model and recent measurements. So, as we know, if we measure the temperature in this room, maybe once after 5 minutes, the temperature between these two consecutive measurements, maybe 5 minutes now and after 5 minutes, another 5 minutes, there might be some relation, correlation. And these predictive coding, they are exploiting that correlation. That is known as temporal correlation. That means within the same sensor, two consecutive or more, like temperature readings or some other readings, they are closely related. So this parameter, like predictive coding can be, they use like statistical modeling, and that statistical modeling can be based on parametric or non-parametric. And for parametric models, they need to know the some statistics. They need to know the environment. They need to have some training data sets so they can develop the model for their predictive coding. And in case of non-parametric, we can use regression. They need very little information about the environment, and most existing schemes in predictive coding, they use parametric modeling. And any predictive coding consists of like 3 different components. One is statistical model, that is a key part of that predictive coding. Second one is learning phase, and third one is model update. And our concentration is the blue one, this is learning phase. Learning schemes in one sensor network, and we are targeting learning schemes in predictive coding. And this learning scheme helps the predictive coding or other techniques to know the parameters related to the parametric model, or that means that the statistical model they are using. And these schemes can be 2 ways. We can use 2 schemes, 2 different ways of schemes. And these are mainly based on gathering and processing, not the learning, like the true machine learning technique. This is mainly based on how we gather data and how we process. So based on the network. It can be centralized, or it can be distributed. Or this distributed scheme, also known as localized scheme. Centralized. In case of centralized one, all the sensors send their readings to the sink or the central base station. This central base station calculates the model's parameters and send them back to the sensors. On the other hand, distributed case or localized case, each sensor gather the training data set and process their model. If needed, they will send it to the sink. Or it can be based on cluster. Cluster can collect the sensor from their neighboring nodes and process the model, send back them to the sensors. If needed, they can send them to the sink as well. But none of these approaches, they don't consider the distance between the nodes and sink. But that could be useful information. If we exploit that one, we can help minimize some energy consumption. So our work is to learn to exploit this distance information. Like using this sample figure, we are trying to analyze 2 existing schemes, which is centralized and distributed. So this network consists of 40 different nodes, and we are making 8 clusters. Each cluster is having 5 nodes. So in case of a centralized scheme, this is the central node or sink. All the nodes will send the information to this guy, sink. And sink will process everything. That is, process everything means we're talking about the modeling. And then sink will send this information to all the nodes. On the other hand, in case of distributed or localized scheme, if we are considering cluster-based approach, if this is the cluster head, then this cluster will collect all the readings from these sensors and process it and send them back again to those sensors. So these are the 2 different existing approaches. But in case of our proposal, we are trying to mix this centralized as well as distributed approach based on some information, based on distance and based on their energy consumption. So we try to analyze this figure based on these 3 approaches. That means the centralized one, localized one, and the possible hybrid one. So this is the 1/2 normalized energy consumption cost for a different running scheme. as we can see from the figure, in case of centralized scheme, the number of one-up communication is 107. And in case of localized one, is 68. And in case of in case of hybrid one, if we mix them these two techniques, existing techniques, based on their distance and some like energy information, we can minimize the number of one-hop communication to 51. So it's clear from this analysis, definitely this is not a like absolute one, this is the approximated one. So it's clear from this table that the hybrid of these two existing schemes has some potential. So we are trying to do that in this paper. So what is our motivations? The first one is saying the distance between sink and its first one-up neighbor can be just like the distance between these two. That means sink's one-up neighbor and that node's one-up neighbor. So if they are almost same, why don't we try to use this sink? Because if this guy is processing model for all these nodes, he might die earlier than like some other nodes like this. So in this case, we are planning to transfer the responsibility of this guy to sink, because sink is more powerful than any sensor node. So it can it's power connected, and maybe it can be a laptop, it can be a desktop, it can be compared to sensor nodes, they are more powerful. So as we have seen in the earlier table that the impact of hybrid approach in communication overhead of learning can be significant, especially in case of large wireless sensor network. If the wireless sensor network is very large, the distance from this sink to the last node can be huge. So in that case, if we suggest to have centralized approach, that means that particular node has to send very long distance. But if there is a node here close to the sink, and it's very short distance it has to cross. So if we apply a single scheme, maybe centralized or maybe distributed, this could give you the suboptimal solution. So our plan here is to exploit this distance information and to have a combination of these two techniques. And importantly, the third motivation is that typically, as we know, typically in wireless sensor network, these nodes are the critical nodes, and these are the bottlenecks. If they do the responsibility of as a forwarding nodes through the sink, as well as some distribution processing, they might die earlier than all the nodes in the network, and that means whole network can be disconnected. So our plan is to get rid of the responsibility of model estimation, especially to these one-hop neighbors, so that they can work as only forwarding nodes or some other critical purposes. So what is the proposed scheme? As we told earlier, that objective here is to hybrid of these two existing schemes and take the advantages of this scheme. And selection scheme, where should be centralized, where should be distributed, it will be based on the distance between the sink and the corresponding node, or that is concerned node, and their energy consumption. So we have two parameters: the distance between the node sink and the corresponding node, and the cost of energy, and cost in terms of energy between these two nodes. And here again, the objective is to find the combination of these two schemes which minimizes or optimizes the overall energy cost of learning in case of predictive coding. And the sink, that means the central node, will be responsible for selecting the model. Which node should use what protocol, what scheme. So it's powerful node, so it can spend some energy in calculating the selection algorithm. This is the selection algorithm. So here n means the total number of nodes, Cn is the communication range between sink and other nodes. For every node, we are calculating the distance between the sink and that corresponding node. And if this distance is less than or equal to the Cn, that means the communication range of that particular sink, that means they are their first neighbor. That means one-hop neighbor. If they are one-hop neighbor, then we are calculating the distance between the one-hop neighbors of sink and these neighbors one of nodes. That is this one. And then we are calculating the corresponding energy. That means corresponding energy means energy for this distance and energy for like sinks one of nodes. If, okay, I have only 5 minutes, so I'll just skip. This is the selection technique. Through this selection process, we'll determine based on the network which node should use what skip. And we use some numerical experiment, and we use 2 data sets. One is the very popular Intel Lab data sets, and another one is synthetic one. As we can see from the figure, this is temperature readings from Intel Lab, and this is like the synthetic data set. This is for humidity. You can see the node 1, node 2, and node 4 and node 1, they have very good temporal correlations. So it means we can apply this data set to our scale. This is the experiment we did. This was done in MATLAB. So this is for temperature reading, and this is the predicted value. The black one is the original signal, and red one is the predicted one. Same as here, black, original, and red one is predicted. So the matching is 94%, and here is 95.6. It's quite good. If you look at this prediction error, normally like in like temperature sensor, we can tolerate like 0.5 plus minus degree centigrade. But the prediction error is almost of the time is less than 0.2, and average is 0.25 or something like this. It's quite good. So as our tolerance is 0.5, and we are having an average of 0.25, okay, it's fine. And same is here. So our scheme is working fine in predicting values. What are the numerical tables? Yeah, you see, this is we are using 2 data sets as I told you earlier. The data set 1, data set 2, and this is the energy consumption in millijoule. This is for centralized approach, and this is for localized, and this is for hybrid approach. The overall energy cost, you see, this is 2.57 for the centralized approach and 1.35, almost just half. In case of localized one, we're saving almost 50%. And in hybrid case, compared to this one, we're saving around 25% or plus minus. I think more than 30%. And again here, the cost of saving between centralized and localized is more than 50%. But here, slightly, very little. And you see, if you compare these 2 figures, 2 values, overall calculations, they are having different performance because the network is different. So our approach depends on the network structure. In this case, we have 54 nodes, and here we have only 40 nodes. So network density is another issue. So for large-scale wireless sensor network, these schemes work better. So the conclusion, in this paper, we tried to develop a mixture of 2 existing protocols that were learning scheme, which are used in predictive coding, and we showed through our results that it has the potential to minimize learning energy consumption cost. And in this particular paper, we didn't consider the processing cost of the model processing cost. That can be a little high, especially in case of large-scale wireless sensor network in localized approach as well as hybrid approach. So we are trying to use develop this or study this issue in our next work. Thank you. If you have any questions.
Now I open for Q&A.
Yeah, I have questions.
Yeah.
Because you want to save the energy, so you use the compression technique to decrease the data to transmit, right? But however, you have an overhead about the compression operation, right?
Yeah.
Yeah. Can you talk about the overhead?
You see, overhead is coming, as we said. In case of centralized approach, the overhead is transferring to the computational overhead is transferring to the sink. And in case of distributed, this overhead is coming to cluster head or that particular one. The cost, like in our approach, the additional cost is coming from the sink because we are doing the processing, the selection method in the sink. As sink is connected to the main power, So we can sacrifice some complexity, some like computational power.
No, but however, actually the compression is occurred in the tensor node.
Yeah.
It's not in the link.
Yeah. So we are expecting that the predictive coding, some other compression technique like distributed source coding, they will take some. For example, as I told you, the policy increase competition at the cost of reduce communication at the cost of increased computational cost, and the ratio between, for example, if we can minimize 1 bit of transmission, we can save, for example, at the cost of 100-bit communication, so computation, that still we are saving maybe 5 times.
Yes, for example, turn to maybe your result, the tables. You can see that in the database, data set 1, the hybrid have less the energy consumption, almost half of the centralized, right? Less than half of the centralized power consumption. So that means the overhead is far less than the decrease of the transmission cost. So that means that your compression cost, energy cost on the compressions is very, very small.
Actually, the cost related to compression, we see in predictive coding, my concern here is not how the cost of compression is working. I'm accepting that predictive coding, some other compressed sensing, web transfer coding, all these schemes, they are acceptable. They are doing their business and they are having some complexity. But I'm accepting all the people, okay? And I have already published a paper in STM transaction in data compression, so I can go further detail, but I don't want to because already I'm overdue. So, but I'm saying that I'm accepting that compression complexity. If I increase the compression complexity 100 times, still in number of cases I can save 5 times computation cost. But parallelly, we're also losing some accuracy. But those information, those things you need to accept. Yeah, this is the bottom line. Okay, we need to accept some loss. We need to accept some compression complexity.
Yeah.
Otherwise, we cannot go ahead because the overall goal is to minimize the communication cost or overall cost, which is mainly dominated by communication. And if we can do that one, then we can increase the lifetime of the sensors. That's our plan. In your point, I'm starting from that. I'm accepting that point that we have some overhead.
Yeah. Thank you.
Okay, thank you very much.
Yeah,
Can we
thanks.
give a big applause? Now I would like to invite